Welcome to online virtual class in General Chemistry for Teachers. I am Janelle Soria, a student in Master of Science in Teaching, major in General Science, and Mindanao State University General Santos City. Before the virtual class begin, let's be reminded of the virtual classroom rules. Here are the rules to follow. Mute your microphone, listen attentively, and use the virtual hand to raise your concern. In this class session, we will discuss about how to balance chemistry education between observing phenomena and thinking in models. At the end of this discussion, you will be able to first discuss how to balance chemistry education between observing phenomena and thinking in models. Second, determine teaching strategies using models. Now let's define first what is chemistry education. Simply, is the study of teaching and learning chemistry. In chemistry education, students have to learn multiple meanings and models, but it is well known that many of them have difficulties in understanding chemistry. Also, it is essential for enhancing the efficacy of instruction, research and development, as well as for ensuring that students have the skills required to produce high-quality products and services that satisfies human needs for food, healthcare products, and other materials that aim to enhance quality of life. These multiple meanings and models in chemistry was formulated the three dominant and interrelated point of view about how teachers encounter difficulties in teaching. So we have the first, which is the social constructivist. In this, learning is a dynamic and social process. Students actively construct meanings from their actual experience in connection with their prior understanding. Knowledge and learning are considered as fundamentally situation-based. Second is socio-cultural. Education is an enculturation process. Learning is considered as a change from a particular socio-cultural environment containing students' everyday life knowledge and experiences to a new socio-cultural environment containing school chemistry experiences and knowledge. This is according to Vygotsky, 1986. This transformation also includes a change of language, and old terms get new meanings. In addition to the former perspective, this viewpoint also emphasizes the importance of using adequate language in chemistry textbooks and classroom practices. Third is conceptual change. Learning is a cognitive process of change of conceptions. Students will incorporate new conceptions with existing conceptions when they conceive them as intelligible, plausible, and fruitful. But they will block them when they see them as conflicting with their existing conceptions. This is according to Posner, Strike, Newson, and Gersdorf, 1982. When students are confronted with new ideas evoking a cognitive conflict in them, this viewpoint implies that teachers use students' dissatisfaction for stimulating them to discard the blocking conceptions or limit their use in favor of adopting new conceptions that are also intelligible but more plausible and fruitful. All three viewpoints acknowledge the important influence and role of initial conceptions that students have when they are involved in learning. Students often use them for developing new conceptions. For example, when explaining chemical phenomena. It is well known that students' conceptions do not always correspond with those agreed upon by the scientific community. Their alternative conceptions often create difficulties in understanding chemistry concepts and processes. Now, it's time to talk about the multiple meanings in teaching and learning chemistry. According to John Stone, 1993, has presented a very influential analysis of the nature of chemistry by distinguishing three related domains of meaning: the macroscopic domain, the submicroscopic domain, and the symbolic domain. The macroscopic domain mainly deals with substances and chemical phenomena that can be observed, smelled, and so on. For instance, sodium chloride, the main component of table salt, will be described as a white or colorless crystalline solid with a characteristic taste and the property to dissolve in water. The submicroscopic domain mainly deals with particle entities, especially atoms, molecules, ions, and electrons, and their arrangements. For instance, the constituent particle of solid sodium chloride can be described as ions of sodium and chlorine that are arranged in a regular ionic lattice. While the symbolic domain mainly deals with representations in terms of formulas, reaction equations, charge signs, and the like. For instance, the dissolving of sodium chloride in water can be described as NaCl solid, which is the sodium chloride, plus H2O liquid, which is the water, to sodium aqueous plus chloride aqueous. The process domain mainly deals with the way any reaction occurs, such as processes of breaking and forming bonds, energy changes, and so on. It can be related to each of the other three domains for acquiring a deeper insight in chemistry. Now, let's discuss further about models and modeling in chemistry. What is model? Model is usually defined as a simplified representation of a target, example object, substance, phenomenon, and process, which concentrates attention on specific aspects of it. This is according to Ingham and Gilbert 1991. The main function of models is to express meanings by providing descriptions of the target, especially when it cannot be observed or measured directly, and by providing explanations and predictions regarding the target. Models are considered to be powerful when they are applicable in a range of contexts and for many purposes. For instance, the idea of particles is very powerful because it is fruitful for explaining and predicting many chemical processes. Models can be designed, tested, revised, and replaced. These activities are called modeling. So when designing models, scientists have to define a compromise between the similarities and differences with the target. According to Justy and Gilbert 2000-2002 and Taubert 2008, models can be classified in several categories: mental model, curriculum model, material model, visual model, verbal model, mathematical model, and combined model. Mental models are the result of internal cognitive activities and are by their very nature private and inaccessible to external world. When they are taken into the tangible world for discussion, they are called expressed models. As soon as consensus is reached, they are called consensus model. This category of models is called scientific models in the world of science. Curriculum models are the often simplified versions of scientific models that are incorporated in chemistry syllabuses as desirable knowledge. Teaching models are constructed for or by chemistry teachers to help them to communicate the curriculum models to students. Next is material models, such as colored plastic, molecular scale models. Example, ball and stick models are used, and space filling models. Visual models such as pictures of atoms or molecules, reaction rate diagrams of reactant concentration versus reaction time, and computer-based animations of processes. Verbal models such as oral expressions, written text, analogies, and metaphors. Symbolic models such as formulas of atoms or molecules. For example, please take a look on the screen. We have here molecular formula of hydrogen 2 and molecular structure of hydrogen 2. For mathematical models, these models such as the Arrhenius equation for chemical kinetics and the equation of the equilibrium constant. For combined models such as a text explanation of a phenomenon with a related diagram or a concept map including text and formulas. Multiple meanings and models are not easily to understand for many school students. Let's determine the students' difficulties in understanding multiple meanings and models. First is the students' difficulties with the relationship between macro domain and sub-micro domain. Solid matter made up of particles that are in close contact without space. Macroscopic properties are explained by attributing these properties to individual particles. Students often believe a single atom of copper has a brown color and a single molecule of chlorine has an irritating smell. They also the reason that the individual molecules of solids are hard while individual molecules of gases are cloud-like. Next difficulty is with the relation between symbolic domain and macro or sub-micro domain. Formulas only represent particles even when a macro symbol is added. For instance, students do not interpret two molecules of chlorine, which is gaseous, as a representation of the substance chlorine in the gaseous state, but as a representation of a single molecule in the gaseous state. Formulas of compound do not represent coherent cluster of particles. Student may consider the formula of H2O as consisting of 2 hydrogen and only 1 oxygen. That is, they draw a diatomic molecule of hydrogen and at some distance an atom of oxygen, or they draw H2O as 3 separated atoms. So there are factors explaining students' difficulties with those models. So number 1, mismatch between everyday conceptions and scientific conceptions. Another factor is the demands of abstract reasoning and the use of complex convention. For example, the chemical reactions are not only taught by transformations of substances but also as rearrange of atoms. So for teacher, there are also factors of difficulties in the part of teachers, especially the teacher textbook factor. So the expertise as a source of students' difficulties. And another teacher's factor of difficulties is they ignoring students' alternative conceptions. So there are teachers are often ambivalent towards the importance of students, the alternative conceptions to their teachings. So another teacher textbook factor is by using misleading verbal and visual models. So sometimes teachers and textbooks are not always very careful in using language and presenting pictures that are clear for students. So another is the curriculum factor. So the curriculum factor, all the chemistry curricula for secondary school address 4 related domains. So they also compromise models, but many of them mainly focus on the content of the models only. They do not pay much attention to the model concept itself, such as the nature and role of models and functions modeling in chemistry. So we have also teaching strategies using models. You can teach about modeling by asking students to carry out modeling activities by themselves. And after their activities, you can point out the steps of process of modeling explicitity. So some simple examples are given the following. First is the 3D structures and properties of substances. Second is 3D structures and structural formulas. You can ask students to build molecular scale models of some inorganic substances. Third is the 3D structures and chemical reactions. So you can ask students to build molecular scale models. And we have also atomic models, combustion models, oxidation reduction models, and acid-base models. So that's the end of my discussion, hoping that you acquired new learnings from my discussion, and thank you for watching. See you again for my next video lesson.